streaming now. Awesome. Okay, so today we're going to talk about proofs, pigeonhole principle, proof by contradiction. I think there's probably like proof by induction and stuff like that as well. Basic proof techniques. All right, we can get started. Okay, so this is the first problem. It's about sequences. Kind of. It uses what we've learned before about sequences and closed formulas and recursive formulas. So let's read the problem together. For the sequence given recursively by AK is equal to 2, AK minus 1 minus 3 for all k greater than equal to 2, where A1 is 4, someone has guessed the closed form and used the predicate Rn for the statement An is equal to 2 to the n minus 1 plus 3. So first of all, if we want to see if we look at A, it's asking us are R1, R2, R3, R4 true? What do we do? This should be simple enough. Any ideas?
You can compute R1, 2, 3, and 4 using the recursive formula, and then compute them using the closed formula to compare.
Yep, that's exactly what we do. All right, so let's start. So if we use the recursive formula, we would get AK. So AK is equal to, actually, do I have an extra page? Yep, I actually do have an extra page. That's good. So AK is equal to 2, AK minus 1 minus 3, right? Okay, so then R1 is basically to calculate A1, which is already given with the recursive formula, which is 4. Right? And then with the closed form formula, we have 2 to the n minus 1 plus 3. Then A1 is equal to 2, 1 minus 1 plus 3. So that's 4. So this one is true. So what about R2? Do some algebra. What is R2? Too early for algebra, I guess. Okay, 2 times 4 minus 3, that's 5, right? Okay, and then on this side, A2 is equal to 2 to the 2 minus 1 plus 3, that's also 5. Check. And shall we do R3? A3 is equal to 2 times A2, right? So that's 5 minus 3, that's 7. And A2 on this side, 2 to the 3 minus 1 plus 3. That's also 7. 4 plus 3 is 7. Okay, last one. What do we do here? What is A4? Yep, that's correct. So 2 times 7 minus 3, that's 11. And then on this side, we have 2 to the 4 minus 1. So 2 to the third is 8 plus 3 is also 11. Yes. So they're true because the left-hand side is equal to the right-hand side. Or like more like the recursive formula is equal to the closed formula. So the first one is true. So we just solve this one. And then let's go for the second one. So write R8 and R9. So what is R8? It's the statement, also the closed form formula. How do you actually write R8? It's equal to what? 2 to the 7 plus 3. 2 to the 7 is
128.
actually, what is 2 to the 7? 128. Yep, 128 plus 3, it gives us 131. And R9, same thing. So actually, this is not good. I should probably write. So A8 plus 3 this. A9, 2 to the 9 minus 1 plus 3, 2 to the 8 plus 3. So that's 256 plus 3, 259. Oh, yep, very good. I see answers in the chat. That's great. Easy? Okay, so this one is the fun one. Suppose that Amanda has already verified R8. Show how to verify R9 without starting over. What does this sound like? What type of part of a proof technique does this sound like?
Mathematical induction.
Yes, exactly. Because we're assuming that R8 is true, and we want to show R9 is also true. Yep, so what do we do? So we already know that, so like, we already know that R8, so how can I say, given R8 is true, want to show R9 is true. So in this case, we have to use the recursive formula that's given to us, right? So since we know that R8 is true, we can substitute. So A9 is equal to 2, A8 minus 3, right? From the recursive formula. So this recursive formula. What do we do now?
Plug in A8.
Okay, so what do we plug in for A8? So, okay, we need to substitute A8 somehow. What do we substitute for A8?
The answer to R8.
What is R8? Yes, we substituted with R8. And what is R8? What is the equation for R8?
The answer is 131.
Sure, we can do that. But okay, so basically we're plugging in this right here, right? This closed formula. So 2 to the 8 minus 1 plus 3, right? Because we know that this is true, because this is R8, right? R8 is true. So we can substitute it in, and then minus 3. We get 2 times 2 to the 7 plus 3 minus 3. And then we just did this one. This is 131, I think. Minus 3, 259. So this step basically substitute R8 in, I guess, R8. Any questions so far? Okay. And now we're going to do induction from the very beginning instead of having R8 to be assumed to be true. Okay, so this is the same exact statement, right? Same exact two statements. And what is, so then that basically means our problem statement is just this. So from here AK blah blah is equivalent is equivalently described by the closed formula this. So this is our problem statement. So yes, P N or P, yeah, that okay. We should probably substitute the K to be N for this to be PN, but they're variables. Okay, so what do we do now? What's the first step? Yes, I see, prove the base case. Yep, that is true. So base case, so what we want to do is show P1 is true. So the recursive formula says A1 is 4, that's given, right? So then with the closed formula, we have A1 is equal to this, which we just did. So base case is true. Oh, whoops. Okay, what do we do now? What's the next step?
Inductive hypothesis.
Okay, what is the inductive hypothesis?
The inductive hypothesis would be assume for some m that a of m equals 2 to the m minus 1 plus 3.
Right, okay, yes. So basically you were saying that the inductive, right, okay. So it is basically true, but this is basic. So inductive hypothesis should be assume that Pn is true, right?
Yeah,
That's our
but
inductive hypothesis.
that
Yeah.
was what Pn was.
So wait, 1 second. So Pn is this chunk that this is our problem statement, right? So what we assume to be true has to be the same as our problem statement. So the problem statement says that the first recursive formula is equivalently described with the second closed formula. So that is the problem statement. So when you assume something to be true, you have to assume this entire thing to be true.
Right, but
that
A
make
of n
sense?
was already defined by the
So like
recursive sequence.
Pn, so what
So
you
you don't
assume
need
to be true
include
in
the recursive definition in the Pn. I mean, I guess you
but the
can.
Pn
You can
should
do it or
be
you
the
don't
fact
have to.
that these two are equivalent.
Yeah. But it is equivalent to say that the two are equivalent and just to say that A of m equals 2 to the m minus 1 plus 3. Because A, by definition, is the recursive sequence. So it's redundant to include the recursive sequence in the P of m. But you can do it both ways.
I guess, I don't know, honestly. So generally you want I don't think anyone would take points off if you say that you assume that AN is equal to that.
Yeah.
Sure, okay, yeah, I guess. Okay, so assume Pn is true, and then the inductive step is what?
So basically you want to prove that Pn plus 1 is true?
Yep, so use Pn is true to prove that Pn plus 1 is true. Okay, so we have An plus 1 is equal to 2. Is equal to what? 2 what?
2 times A of n.
A of n, yep. So basically it's n plus 1 minus 1. Right?
Yeah. Yeah,
And
that's
then minus
better to
3.
do.
An minus 3. So what do we know about An? What do we do now?
Because we assumed Pn, we know or assumed that An can also be equivalently described by 2 to the n minus 1 plus 3.
Great. So substitute in an, we get 2n minus 1 plus 3 minus 3, right? So these two are equivalent based on our inductive hypothesis. And now we just do some algebra. 2 to the n plus 3. And that is exactly what we want.
Oh yeah, so when you do a substitution of the inductive hypothesis into the inductive step, do you have to write out that you're doing that you say like by inductive hypothesis this?
I think in a formal proof, you should. Right, so generally I'll probably write just, even if it's just on the side, I think it's still fine. So if you say that by inductive hypothesis, substitute sub an or something, like substitute in an, just to show that what you're doing and how you're, like why you're doing this.
Yeah. Yeah, I should have
Yeah.
written the substitute part in my homework.
I still don't think so. I think in a quiz, it's probably better to write it. In homeworks, I don't think we will take points on for not writing it. Nancy, what do you think?
I think either way is fine for me.
Yeah, I think so too. Yeah.
Okay.
And I think there might be confusion about like, shouldn't you start with a sub k plus 1 instead of a sub n plus 1?
Yeah, the problem is that because we're saying Pn is true, sure, we can do.
Because you want to end up with a sub k plus 1 is equal to a sub n plus 1.
But does that matter? If let's say like you know what I mean? It's like, okay, let's say that if we start with a sub k plus 1 and we get 2 times a sub k plus 1 minus 1, right? So you get this same like recursive formula, and then you get 2ak minus 3.
Based on the hypothesis, your a sub k equals to a sub n. Then you substitute your a sub n.
Sure. But does that matter? That's like, I guess my question. Like, would that be something that's important?
I just feel it's more clear to say we start from a sub k.
Sure, because this formula right here is given by a sub k.
Yeah.
Okay. That's fine. So still the same thing, by inductive hypothesis. We can substitute in, same thing.
And you can always use a third variable if you want.
Yeah. We're just trying to keep it simple, I guess.
Yeah.
Okay, any questions?
It's all equivalent in the end anyway.
Yeah.
Would it matter if I prove it like the other way? I started from the recursive formula and then I proved that. Oh no, I proved the closed formula and then I get the recursive is true as well.
So wait, but that's not using induction anymore, is it?
Oh, but I use that Pn is true. Okay.
Nancy, what were you gonna say?
Saying like start from the closed formula to show.
Wait, Nancy, what were you going to say?
Yeah, I think he's trying to start from the closed formula, like a sub n plus 1 equals to 2 to the n minus 1 plus 3 to get to a sub k plus 1, like the other way around. Because right now we're starting from a sub k plus 1. Is that what you're saying?
I think my internet is really bad.
Yeah,
Anyway.
I was writing something. Yeah, I was saying that.
Okay.
Okay. Good.
Yeah, since the problem statement uses the words equivalently describes, I think you can go both ways. So you can start from the closed formula and prove that that you recover the recursive formula, or you can start with the recursive formula and go the other way. You just need to make sure to do the induction right. I think is the most important part.
Okay. Okay, let's talk about pigeonhole principle. This is fun. Given any 5 integers, there will be 2 that have a sum or difference divisible by 7. What do we think? What do we do? Any ideas? You can type in the chat or say something.
So I guess
So there is a
the number
ahead.
of categories is going to be 5 minus 1. Oh wait, no, that's not it. Oh wait, yeah, that actually is it for this case. So the number of categories is 5 minus 1. So we need to
right,
come
but
up
how
with
do you do
those.
that? Right, okay, so there's a theorem in the book that says, it's on page 143, that says if mn plus 1 objects, so this is the number of objects,
and then m is the, oh, go ahead, sorry.
are distributed among n different boxes. So n is the number of boxes. So n number of boxes. Then there must be some box containing at least m plus 1 object. So some box that contains m plus 1 objects. So in this case,
So that's how you get to it.
we have mn plus 1, so that's a number of objects, right? So we have 5 integers, and that's our objects. So 5 integers, so then that means this is equal to 5.
And then the at least 2
Yep.
is the m plus 1.
Yes, so number of objects here. And then we have to have at least 2 in each box. So then we can solve for an m and n. So here is easy, right? M is equal to 1. Immediately we see that. And then we plug in m here in this equation. We get 1 times 4 plus 1 is 5. So n is equal to 4. And we see that n here is defined as the number of boxes. So that means we have 4 boxes. 4 boxes, or like 4 categories, however you want to describe that. Here we have 4 boxes. Any questions about that? So this is, I think, page 143, theorem 8. Yep. Okay, then let's keep going. So we have 4 boxes. So how do we want to distribute? So like, what are the, what do we want to do next? Like, what do we think? So it says that there will be 2 that have a sum or difference divisible by 7. So this is the key part. It says divisible by 7. So what are the different types of cases when you divide a number by 7? What can we get?
You can get different
Do we have a reference?
Sorry.
Wait, 1 second. Someone's asking, do we have a reference? Do we have to reference the theorem on quiz? No, you don't. As long as you can figure it out, it's fine. I'm just like letting you know that that's where it is if you need to go find it. Yes, very good. I'm seeing answers here. Yes, exactly.
yeah.
Right. So we use the division theorem. So we have n is equal to 7k, 7k plus 1, 7k plus 2, 7k plus 3, 7k plus 4, 5, and 6. So we have 1, 2, 3, 4, 5, 6, 7. We have 7. So all the integers has to fit in one of these categories. So how do we put these 7 different cases in 4 boxes? What do we do?
I can't remember why, but I think you can pair up the ones that aren't just like a perfect division. So +1 with +6 and +2 with +5 and +3 with +4.
Yes.
But,
So
yeah.
I also see an answer in the chat. Yep, that's correct. And then, but the reason is that we want, so you have to look at the problem prompt. It says you want a
yeah.
sum or difference divisible by 7. So you're
Yeah.
trying to find ways to make things the sum or a difference divisible by 7. So if that's the case, if we pair up these two, then their sum becomes 7k plus 7 if they're different, right? And then when they're the same, if they're both 7k plus 1, if you have two integers that are both in the form 7k plus 1, then you can have like 7k1 plus 1, and there's 7k2 plus 1. So that would also be divisible by 7. So all that you want is to find ways to put the sums and differences together that these two numbers would give you something divisible by 7. So now we can put these in boxes based on the reasoning that I just gave. So then I guess box 1 can just be 7k. Here. Okay. Box 2 would be 7k plus 1, 7k plus 6. Box 3, 7k plus 2, 7k plus 5. Same reasoning, 2 plus 5 is 7, right? And then box 4, 7k plus 3, 7k plus 4. Right, so these are our boxes.
I have a question.
So go ahead.
Is this only for the sum? Do we have to do like the difference later?
So there are going to be cases where you will see that both the sum and the difference will work, right?
Oh.
So like if you given different cases, that sometimes the sum will work, sometimes the difference will work. So it just depends on like what happens with the integers you were given, right? Because you're given 5 random integers. You don't know what type of integers you will be given.
Right.
Right. So sometimes it will be the sum, sometimes it will be the difference. And then for things like 7k, right? Imagine, like, think about it. If you get two integers that both land, if you get like two integers that land both in box 1, then there are two integers can be written something like 7k1 and 7k2, right? So these are like the two integers that you get. So then both the sum or difference will work. Right? In this case, you get 7k1 plus k2, and this one you get 7k1 minus k2, right? So like both the sum and differences will be divisible by 7.
Okay.
Does that make sense? Yeah, so you have to argue all the cases possible to show that either the sum or the difference will be divisible by 7. But then how do we know that two integers will end up in the same box? There will be at least two integers that end up in the same box. How do we know that?
Because it is there are only 4 boxes and 5 integers. So
yes, exactly. Right. So the worst case scenario, you get the first integer land in box 1, second integer land in box 2, third integer land in box 3, fourth integer land in box 4, right? That's the worst case scenario. And then there's going to be one more integer that has to be in one of these 4 boxes. So it has to land in one of them. Yep, that's exactly true. So I just basically did the first case for us. So let's say that the first case is that the 2 integers are in box 1, right? So case 1, so this is basically, let's not say case 1, let's say let's just do if box 1 has 2 integers, then their sum would be this, right? So let's say that's equation 1. Which is divisible by 7, right? And then you can say the same thing about their differences. So, this would be their difference. So that's the first scenario, right? So this is kind of like a special case, right? So box 2, 3, 4 are similar in ways. So let me write this again. Okay, so what about box 2, 3, and 4? So these are similar. So you can kind of, so to be safe, you can argue that each case, argue each box separately. But I think in our case, I can just kind of show us how to do any one of them, and then they would just be the same. So with box 3 and 4, with box 2, 3, and 4, there are 2 cases, right? So case 1 is that if the 2 integers have the same remainder. So that's case 1. If the 2 integers to land in each of these boxes have the same remainder. So the 2 integers can be written as 7k plus r, 7k1 plus r, and 7k1, k2 plus r, right? These are the 2 integers. Yes, I see the answer in the chat. Yes, that is correct. But you do need to argue how you got there, right? So how can you write them as 7k plus 7? And then, right, okay, so let's keep going here. So if we have case 1, if the 2 integers have the same remainder, then how do we get something that will be divisible by 7? Is it sum or difference? Yes, then their difference make it divisible. Yes, that's correct. So their difference would be 7k1 plus r minus 7k2 plus r. So that gives us 7k1 minus k2. So by closure of integers, we know their difference would be divisible by 7, right? So then the second case, what is the second case? What is the second case? Right, it's different. I guess you're trying to say that their remainders are different. Yes, okay. So if the two integers have different remainders, then the two integers can be written as this, right? These are the two integers. So now notice R1 plus R2 is equal to 7 in all, actually, in all boxes 2, 3, and 4. Right? So then their sum would be 7k1 plus R1 plus 7k1 plus R2. And that gives us 7k1, 7k2 plus R2. K2 plus 1. So their sum is now divisible by 7. So on a quiz, I would suggest how about writing R2 as 7 minus R1? Sure, you can do that. Either way, it's like you're just trying to show that the remainders, when the remainders are different in each of these boxes, the remainders add up to 7. So then you can get something that looks like 7 K1 plus K2 and plus 7. That's what you want. So I think in a quiz, it will probably be safer if you actually argue in box 2, this happens in box 3. So you list the 2 cases for each box. But I don't think this would be wrong if you argue them together because they are very similar. Any questions? So I think the most important thing to remember is that theorem 8 on page 143. So you can figure out the number of boxes and then you can figure out, how many things need to be in the same box. Okay, this one's easy. Prove the following by using contrapositive. For all real numbers x and y, if x squared plus y squared is not 0, then x is not 0 or y is not 0. What is the contrapositive, first of all?
The contrapositive would be if x squared plus y squared is equal to 0, then x and y both equal 0.
No, that's the converse. It's not positive. What is the contrapositive? So if P implies Q, what is the contrapositive?
Q and not P.
We're not negating it. That's the negation of P implies Q. Contrapositive would be not Q implies not P. Contrapositive is going backwards. And these two are equivalent statements. So converse is not the equivalent statement. So if we have this to be the contrapositive, what is the statement? Not Q implies not P. What is the statement? Yes, I see it in the chat. That is correct. If x is 0, if x equal to 0 and y is equal to 0, then x squared plus y squared is 0. Yep, that is the contrapositive statement. And that's simple to prove, right? If x is so, let x is equal to 0 and y is equal to 0, then we have x squared plus y squared becomes 0 squared plus 0 squared, which is 0, right? And that's QED there. And because we proved the contrapositive, that's the same thing as proving the original statement. That's the equivalent of proving the original statement. Any questions about this one? Do we have to change anything about the for all real numbers to x and y? No. So that's like a condition, right? That's a condition. So the condition doesn't change for a contrapositive statement. The only thing that changes is the P implies Q part. So P implies Q part starts with if something happens, then something happens, and the condition stays the same. Any other questions? Okay, that was an easy one. This one shouldn't be too hard either. Use induction to prove the statement. What do we do? What's the first step? Proof by induction. First step. What is the first step?
It would be base case.
Yep, prove the base case, right? What is the base case?
So it is when n is equal to 1.
That is correct. So prove P1 is true. So then this would be I is equal to 1 to 1, 2 to the 1, 2 to the I minus 1. And that is just 2 to the 1 minus 1, which is 1. And then on the other side, we have 2 to the 1 plus 1 minus 2, and that is 4 minus 3, and that is also 1. So base case is, oh, whoops. So base case is true. What do we do now? What's the next step?
The inductive hypothesis.
Yes, exactly. Inductive hypothesis. And what is the inductive hypothesis? What do we assume to be
Pn
true?
is true.
So assume Pn is true. And Pn is basically this statement right here. Right? And then what is the inductive step?
Then prove Pn plus 1 is true, right?
Right. So yes. So there is an answer in the chat that says prove that Pn minus 1 is true. So you need to prove the next one. So if you want to assume that Pn minus 1 is true in the inductive hypothesis, you prove that Pn is true. So basically, these are the two ways that you can do it. So it's either Pn minus 1 implies Pn or Pn implies Pn plus 1. You can choose whichever. Sometimes one is algebraically simpler than the other, but they should be very similar. They shouldn't actually make that much of a difference. So the inductive step here would be since we assume that Pn is true, we're going to prove that Pn plus 1 is true. So what do we do now?
Write down the formula on the left-hand side and put it n plus 1, right?
Yep, exactly. So we have the sum of I from 1 to n plus 1 and 2 to the I minus 1. Oh, we should probably write parentheses to be clear. And this gives us. So what we want is to substitute what we know, right? So we assume that Pn is true. So we want to substitute this thing somehow inside. So then what we do is just to take the last term out plus the last term, which is 2 to the n plus 1 minus 1. This is the last term. Does that make sense?
Yeah.
Okay, so what do we do now?
I think substitute the from I for 1 to n with the 2
Yep.
to the power of n plus 1 minus 1.
Yep, exactly. That's exactly what you do. You substitute this part in because we already assumed that this statement is true for Pn. So we substitute it in, we get 2 to the n plus 1 minus n minus 2 plus 2 to the n plus 1 minus 1, right? So then we get 2 times 2 to the n plus 1 minus n minus 3. Actually, sure, minus 3. And that gives us 2 to the n plus 2 minus n plus 1 minus 2. So this part is a little weird. It's just algebra, but you can kind of write it like this. Maybe this is easier to see. And then you just put a parentheses around the n minus 1, so you get this n plus 1 term. And that is exactly what you get when you plug in n plus 1 as n in here.
Should we always like write like what we want to prove, like Pn plus 1? So we just write, we plug in n plus 1 into the right-hand side so that we know our goal.
Yeah, I think that would be a good idea to do. I do that a lot just to see how it looks like. So in this case, like what we want, so I'll sometimes write like what we want is 2n plus 2, right, minus n plus 1 minus 2. So then when you get to where you want to go, you know that it is exactly what you wanted in the first place. Yeah, and then I think it's a good idea to always write down what you're looking for, so you know, like in the steps where you want to go, and then you try to put it in the form that is your goal at the end. Okay, so this is the end of our time, but if you have any questions, you can ask now. If not, then have a good day.